Lesson 4.2, the natural number. This is a very short section, really only one learning target, and it's an extension of the previous lesson. Lesson 4.1, we talked about compounding interest, where the interest may compound once a year, that would be annually compounding, or it may compound twice a year, could compound monthly. Anyway, if the number of compounding cycles continues to increase to where it's compounding at every moment of time, that's called continuously compounding interest, and it has a slightly different formula. So quick introduction to what's called the natural number. The natural number is called the natural number E, and E is just a symbol that represents an irrational number. It's kind of like pi, and we're all familiar with this symbol. Pi is approximately 3.1415. So E operates similarly. It's a symbol that represents approximately 2.71. And here's where that value comes from. If you look at this table here, there's an expression 1 plus 1 over n to the power of n. That's this expression right here, 1 plus 1 over n to the power of n. I'm going to talk a little bit more about this here in just a second and how it relates to compound interest. But for increasing n values, I want to talk about what's happening to this value here. So if you plug in a 1 for n, you have 1 divided by 1, which is 1, and then 1 plus 1 is 2. 2 to the first power is 2. So when n equals 1, this expression has a value of 2. When n equals 100, this expression takes on a value of 2.7048. If you continue to increase to 10,000, it's 2.71815. If you continue to increase n to 1 million, it's 2.71828. If this process continued indefinitely and n approached infinity, then this expression approaches this value 2.71828. Anyway, it's an irrational number, and it's called the natural number, and it's given the symbol E. E, most likely for exponential. It was discovered by the mathematician Leonhard Euler. Euler spelled E-U-L-E-R, so it's also called the Euler number, or the natural number. Anyway, so this is what you need to remember about E. E is approximately 2.718. Now E is most often used as a base in exponential functions. And we talked about exponential functions in section 2.1. Remember, an exponential function isn't just one where it has a base and an exponent. It's where the variable is the exponent and E is the base. So again, E is most often used as a base in exponential functions, whereas E to some power. And you can graph it just like an exponential function. This would be the graph of y equals e to the x, and it's the same thing that we talked about in lesson 4.1. It has a horizontal asymptote, we find the y-intercept, and a couple of other points. So you can still graph it the same way as any exponential function. It's also used in compound interest. Now here's where compound interest and E are related, and this isn't something you're ever going to have to be tested on. I just wanted to show you where the continuously compound interest came from. So this is compound interest. This is what we talked about in the last lesson, section 4.1. Okay. If I rearrange this formula slightly and remove this power of t and then divide n by r, which means I would have to then multiply t by r, which is what I did over here. I divided n by r, remove the exponent of t to another set of parentheses to multiply by here by r, and I haven't changed anything because if I have this r divided by this r, they're going to cancel out. So it's still raised to the power of n times t. I'm just slightly modifying the formula here. And then if I make a substitution of variables, if I say m now is going to equal n over r, now this is going to be raised to a power of m. That's m for mouse. So this is raised to a power of m now. And then r over n is the inverse, or the reciprocal rather, of m. So this is going to turn into 1 over m. And that's what I have here, 1 plus 1 over m to the power of m. And if you remember, this is the expression that generates the exponential e as m approaches infinity. And this is the number of compounding cycles. So as the number of compounding cycles of the interest increases, this is going to approach infinity, or m is going to approach infinity, which means e, this expression gets replaced with e. So it's going to be p times e to the rate times time, or this formula here, p times e to the rate times time. Remember, e is that irrational number 2.718. And this is the continuously compound interest formula. So when the interest is compounding at every instant or continuously, then you use this formula for compound interest rather than this formula from the last lesson from 4.1. So the continuously compound interest formula is here. P stands for principal, and R is the interest rate, and T is the number of years of the investment. E is not a variable. You don't replace anything in place of E. There's an E button on most calculators. If you're going to replace E with anything, it would be 2.71. But most scientific calculators just have an E button that you can use. So as an example, this is the one that we looked at in the last lesson, 4.1, but in that one we compounded the interest, I think, monthly, and so n was equal to 12, but now we're going to compound continuously. So n is infinity rather than n equaling a certain value. Like if it said monthly, n would be 12. If it said annually, n is 1. If it's compounding continuously, we use the modified version for compound interest, which is principal times e to the rate times time, where the principal is $10,000, the rate is 4% or 0.04, and time is going to be 20 years. So plugging this in, we'd have the amount after 20 years. It's going to be principal investment, which is $10,000, times e to the 0.04 times t. And again, depending on how comfortable you are using your calculator, you may not want to type this whole thing in at once and hit enter, unless you're comfortable with it. If you're going to break this down into pieces, you would evaluate this first, 0.04 times 20, and then use that as an exponent for e. And like I said, most scientific calculators have a base e, so it would be e raised to that power, and then you multiply that by 10,000. When you evaluate this into your calculator, you're going to get $22,000. Let's see, it was 55, and I think it was 41 cents. So $22,255.41. And then when we think back to the same problem from lesson 4.1, when it was compounding annually, it was slightly less, not too much less, because remember, the number of times it compounds doesn't greatly affect money growth. It's the interest rate or how long you leave it in. So if I remember right, when it compounded monthly, it was $22,226. So we've increased to $22,255 by continuously compounding this. So again, not a huge increase, but it does affect money growth if you compound it more often. Here we're compounding it at every moment of time. And that's really all you need to know for section 4.2 is what the natural number is here and how to use it in terms of continuously compounding interest. We're going to see a little bit more of the natural number e in subsequent lessons, 4.3 and 4.4.